Hi students, good evening to all of you. Today I, Sumit Kundu, a graduate from IIT Bombay in civil engineering, would be taking up the session on work energy theorem students. All right. Now students using work energy theorem, all right, solving of mechanics problems kind of becomes pretty easy because the typically whatever the problems that are there, we could either solve it by the energy method or the force method, students. Now the force method typically becomes a little more cumbersome, or let's say complicated, all right. However, because force is a vector quantity and dealing with the vector quantities, the calculations and everything becomes a little more tedious. So using the work energy theorem, you could solve the same questions, okay, by dealing with the scalars. Okay, guys. So today's focus is going to be primarily looking at what is this work energy theorem, the very basic theory, all right. And after that, we'll take up a few questions. Okay, guys. So let's get started. Are you all excited? Chalo. Now, before I could go ahead to explain to you your work energy theorem, primarily I would like to talk about your conservative and non-conservative forces, guys. Okay, now what is a conservative force? Typically, the examples are like gravitational force, electrostatic force, magnetic force, spring force. These are what my conservative forces. And my non-conservative forces are typically the friction force, the viscous force, air drag or air resistance. All of these are my non-conservative forces. Now, what is the basic nature of the conservative and the non-conservative forces? Let me just explain that to you. For a conservative force, work done, whether you kind of take it via this path or this path or this path, from point A to point B, it actually doesn't matter. All right. That means if you have got, let's say, any pen, let's say, I mean, like, my pen out here, I take it from this height to this height. All right. I take it this way or I take it this way. The work done in each of the cases is going to be the same, my dear students. All right. And the second property, all right, is that the work done in a round trip is actually equal to zero. All right, the work done in a round trip is equal to zero. As a result of which, potential energy is defined for a conservative force field. The potential energy is defined. Clear, guys? However, for a non-conservative force, the work done in a round trip, all right, the work done in a round trip is not equal to zero, my dear friends. Okay. Now, same, I mean, like a simple concept that I can talk to you about is, say this block has to go from point A to point B, my dear students. All right. Now here the friction is going to act in this direction. So it is F. All right. And let's say the distance between A and B, okay, say the distance between A and B is given as some value X. All right. So the work done in going from A to B is going to be minus Fx, because frictional force is acting towards the left and the displacement is taking place towards the right, guys. Okay. As a result of which the work done is negative. Clear? Now, why we come back from B to A? So that is completing my round trip. So work done in going from B to A. Now, as it is going to go from B to A, now the friction is going to act towards the right. All right. So again, the total work done. So the work done in going from B to A is going to be minus Fx. Students, the work done in the round trip here comes out to minus 2Fx, which is not equals to 0, which implies I cannot define a potential energy. All right, potential energy is not defined. Okay, guys. Now here I would like to state one thing. It's an important formula that whatever is the work done by a conservative force is equals to negative of the change in the potential energy. And my dear students, this is a very, very important formula out here. Okay. So that is our very basics that we got to study about your conservative force and non-conservative forces. Okay. And going ahead, we are going to talk about primarily a little bit about the work energy theorem. Okay. And after that, we are going to take a few problems and discuss on them. And students, I mean, I've been teaching for so many years now. All right, I have understood one thing, that in mechanics, if you are able to apply the work energy theorem very, very judiciously and smartly, it makes your life kind of very, very simple. Okay, technically, any question, given any question in work energy theorem, in like, related to energy and work and energy, you should be able to solve after today's session. Okay, so that's the problem which is already here. So let's just talk a little bit about your work energy theorem. Okay, guys, very simple. I mean, the work done by conservative forces plus the work done by non-conservative forces plus the work done by the external forces is nothing but equals to change in the kinetic energy. This is as simple and straight as that. Okay, guys. Now, here I have an extension to this work energy theorem that is very simple again. If, my dear students, the observer, now let me tell you first of all, work and energy, these two physical quantities are reference frame dependent. Okay, so in case if the observer is present in a non-inertial reference frame, okay, then along with conservative, non-conservative, and external force, we would be applying a pseudo force to our system. Now, in that case, so work energy theorem, work energy sorry, there's been a slight mistake here with respect to the spelling. It is REN. So work energy theorem. THEOREN in non-inertial frame. In that particular formula, besides these forces, we'll have to include work done by conservative plus work done by non-conservative plus work done by external plus the work done by pseudo force. All right, this is equals to the change in kinetic energy. So that is the only addition. And remember, students, kinetic energy is basically a function of velocity. So here, the velocity is with respect to inertial frame. And in this case, when we calculate my kinetic energy, then the velocity is with respect to non-inertial frame. That's the only difference that you need to take care of. Okay, guys. So what are we waiting for? These are the only two formulas that we need to keep in mind, and any question can be solved. Okay, let's just have a look. So here we take our first question. I've got a small ball of, let's say, mass m. Okay, it is released from this particular height here, students. Okay, and it is moving on a smooth surface. That is very important. Okay, now find the speed when it reaches the horizontal part of this surface. So it's kind of reached the horizontal part, let's say out here. So that is from this part onwards, it is kind of horizontal. Okay, guys. So very simple. This is a very simple problem, by the way, students. It is just to explain the very, very basics. Okay. So here, what is the work done by the conservative force? mg force is typically acting in the downward direction, students. All right. Mg is downward. Clear? And the block is, or the ball is actually kind of going downwards. Okay, so it is going to be just mgh. All right, so that is the work done. And there are no non-conservative forces involved here, so work done by non-conservative forces is 0. Also, there are no external forces involved, so work done by external forces is 0. So adding up all these three, I get just mgh. This should be equals to the change in the kinetic energy. Initially at this point, the velocity is equals to 0. So change in kinetic energy, if I have to consider the velocity out here, so this is like V final, all right, and let's say this was my V initial, then my dear students, that is like half K V final square minus V initial square, which is nothing but half K V final whole square. Okay, sorry for that slight mistake out here. This is not K, rather this is your M. Okay, that is the mass. Half M V final square minus V initial square. Okay, and since V initial is equals to 0, my dear friends, this is just equals to this, then I can have my M and M deducted, which implies my V final is equals to root over 2gh. All right. So that's a very simple question. All right. This is just like when we kind of lift up a ball in the air and we want to calculate what is the velocity at a given height. It's a similar result that we are kind of getting here. Okay. Now, students, we will tweak this particular question a little bit. Okay. What we will do is in the horizontal part, we are going to keep a spring. All right. And then we are going to calculate what is going to be the maximum compression in that particular spring. Okay, guys. So again, we will do by the same method, work done by the conservative force. Students, another way of looking at it, work done by the conservative force is minus delta U. Okay, guys. Now here, what are the forces involved? We have got gravitational forces, number one. We have gravitational forces, and students, besides that, we have got spring force. All right. So potential energy is kind of defined for both of them. All right. So here when I calculate this, it is minus delta U gravitational plus delta U spring, my dear students. Okay, so what can I write this as? This can be written as, all right, U gravitational initial minus U gravitational final plus U spring initial minus U spring final. Okay, so students, if I have to calculate this, what do I do? Very simple. Initially, this ball is at a height, and after that, when it is hitting this particular spring and going ahead to compress it, then it is at the horizontal level. Okay, so initial potential energy is mgh. Final potential energy is kind of 0 plus. What is the initial spring energy? Initially, my dear students, the spring does not have any elongation or compression. So the spring energy is equals to 0 initially. So this is equals to 0. But later, let's say it gets compressed by some value x. That is the maximum compression. Okay. So it is going to be minus half k xs squared. All right, students. Now, this is my total work done by the conservative force. There is, I mean, like, none of the surfaces, I mean, it's all a smooth surface. So there's no roughness out here. So there are no non-conservative forces, no external forces. So overall, I have this as the total work done by the conservative force. That is mgh minus half kx squared. Then students, this is nothing but equals to the change in kinetic energy. At this point here, velocity is 0. And finally, when it is compressing the spring and then going finally to stop, there also it is at rest. So the final velocity is also 0. Then the change in kinetic energy, my dear students, is going to be equal to 0. Okay. Now, from this information that we have here, we will have to calculate what is the value of x. Okay. So x is going to be nothing but root over 2mgh upon k. So that is, my dear students, the max compression in the spring. Okay, I hope everybody has understood how we are applying the concept of work energy theorem to the basic problems out here. Students, this is exactly what we have to do, even if, like, we get across as a complicated problem, a complicated situation. Okay, so let's just go ahead and let's explore a little more. Okay, students, I'll come back to this problem, which is given out here. We have to find out the maximum elongation in the spring. But I think more than this question, okay, you would be interested in this one. Okay, let's just take it up. Clear? So here I have got a chain of length L, which is being told to me, and it has got a mass M out here, and it hangs over the side of the table to anchor her. All right, guys. Uh, what are they asking us is, okay, slowly it will start to slide down. Okay, and there will be a stage. So let's say another diagram. Let me just draw it here. So there is going to be a stage where this will be sliding down the table. Okay, guys. This will just be sliding down the table out here. So at that particular instant, they are asking us how much is going to be the kinetic energy of the chain. Okay, so out here, my dear students, L length is going to be hanging. Clear? Though it is not proportional, but here, just to give you an idea, L length is hanging, and here, from here to here, it is just L by 3 which is hanging. Students, if I have to do this by force method, just imagine, all right, how difficult is this going to be? Okay, but doing it by the work energy theorem, it is kind of very simple. All right, let's just have a look. Now, they want us the final kinetic energy of the chain. We'll have to go ahead and define something. See, at this level, the potential energy is equal to 0. All right. Now, final kinetic energy I have to find out. Initially, the chain was just resting on the table and there was no motion. So, kinetic initial is equals to 0. And final kinetic energy is what I have to find out. Okay. So, delta K is nothing but the final kinetic energy. Clear, guys? Now, is there any friction? It's a smooth table, very clearly, which is mentioned out here, my dear students. It's a smooth table. So there is no friction, there is no non-conservative force, and there are no external forces. So we just have to calculate what is the work done by the conservative force. And we know work done by the conservative force is equals to what? Yes, correct. Work done by the conservative force is minus delta U, which is nothing but equals to U initial minus U final, guys. Okay. Now, what is U initial? This is the initial stage. So, this portion out here is resting on the table. It's potential energy. However, whatever must be lying out there. Okay. So, the total length of this chain is L. That corresponds to M mass. Okay. The part which is kind of resting on the table, that is how much? 2L by 3. So its mass will be 2M by 3. And students, the part which is hanging, it is just L by 3. So corresponding to that length, its mass is M by 3. Okay. Mass is uniformly distributed over the entire length of the chain out here. Okay. So students, U initial, let us calculate that. What is going to be my U initial? The initial potential energy. What is the mass of this chain out here? M by 3. Where is it going to lie? At the center of mass? Where is the center of mass? At minus L by 6. This from here to here is L by 3. So it is just at its center. So that is like what? L by 6. So my dear students, U initial I can say it's minus M by 3G into L by 6. Okay, students. And then I'm going to calculate what is my final potential energy. While it is a final, then my dear students, the entire chain is just about to fall. So its total mass is going to be like M. And where is it actually positioned? The center of mass at L by 2. Okay, guys, or let's say minus L by 2. Then its potential energy is going to be minus mg L by 2. Then as per what we want to calculate as the work done by the conservative force. So work done by the conservative force is going to be like mg L by 2 minus mg L by 18. Okay, students, I'll take 18 as the LCM out here to 9 times. All right, and 18 1 times. Okay, so this is going to be like 8 mgl. Okay, that is going to be your LCM out here. That's going to be the final thing. So this is like 2 4 times and 2 9 times. So the final result is 4 mgl upon 9. My dear students, that is going to be the work done by the conservative force, and we know that is the work done by the conservative force is delta K, which implies my final kinetic energy is going to be equals to 4 mgl upon 9. I hope students this idea is very very clear to all of you. Okay, so we will kind of move ahead to our next problem here. I hope you're enjoying the session so far and you've learned pretty much how we apply or what is the work energy theorem and how do we apply it to different problems in the scenarios that we are just seeing here. Okay, so guys, you're feeling more confident about work energy theorem now? Okay, chalo, great. Let's go ahead. Now, here I have a very, very interesting problem, students, and I'll take some time to discuss this problem. Okay. Now, here they are asking us that this is the arrangement we can see here. There is a block of mass, capital M, which is attached to a spring. Okay. And there is a small block of mass, small m. It is going to fall from a height h. Then they are asking us what will be the value of h such that when it falls from that particular height and then it is going to like compress and then again bounce back, okay, such that this block capital M is going to lose contact, okay, it is going to lose contact with the ground. Okay, students, when the thought comes that it is going to lose contact with the ground, all right, what is the first idea that comes to my mind? That at that point, whenever it is losing contact, my normal reaction force will be equal to 0. Okay. Now here, let us discuss the problem in steps. Okay. So here I have this diagram, which is very, very clear. So this is the height of mass small m. So that is the small m here and capital M. What I've tried to show is this is the initial when I have not even made it fall. And then it kind of falls and it is right now just touching it. It is not yet compressing the spring. Okay, guys, it is not yet compressing the spring. So it is just lying on the spring. So there is no force exerted on it, no compression, nothing. Now here it gets compressed, say by x1, right? Students, if it gets compressed, then definitely at this time, the spring force on it is in the downward direction. Okay, the spring force is going to be in the downward direction, and here on this block, it is going to be the upward direction. All right, so definitely when it is getting compressed, all right, students, when it is getting compressed, then the bottom block is definitely not going to lose contact with the ground because it is being pushed. All right. So definitely this at the second instance, it is not going to lose contact here. Now let us understand what is going to happen such that it loses contact. So if it kind of the spring gets pushed, okay, it is going to come back to its natural length once again. It is going to come back to this. But is it going to stop here? No, it is not going to stop here, my dear students. Rather, after it has reached the normal length, okay, once again, it is going to bounce back and go up to a height, let's say x naught. All right. Now here, as it goes up, my dear students, on the top block, it is going to pull down, and the bottom block, it is going to pull up. All right, students. Then what is my free body diagram at that instant I can look at? What are the forces acting on it? Spring force, upwards, kx, normal, upwards, kx, equals to mg. Sorry, yeah, that's right. So students, here the equation will be n plus kx equals to mg, my dear students. Is the idea clear to all of you? Now here, if it loses contact with the ground, my dear students, come, focus here. If it loses contact with the ground, then my normal reaction for students will be equal to 0. Then in that case, my kx will be equals to capital N G, which implies my x, or let's say I have taken it as x naught, so I'll take it here as x naught as well. So my x naught will be equals to capital mg upon k. Okay guys, so this is going to be the formula for the extension in the spring that is going to allow the greater block to lose contact with the ground, students. Okay, now what else, like, how do you find out from what height I should kind of throw it? So for that we will be using our work energy theorem, and I'll take the next slide to explain that to you, students. Students, are you still interested to go ahead? Yes, I think so. Yes, you are. So let's just go ahead and explore that once and for all. Okay, so students, here initial and final stages is what I have to define. Okay, because for what? Change in potential energy or change in kinetic energy, for that change I should know what is the initial and what is the final, right? So what is going to be my initial and my final? That's what I'm going to judge here. So my initial is this: when this block is at a height h, this is my initial, and my final is this when it is when the extension in the spring is x naught. This is my final. So in intermediate, this is not my concern. Whatever is happening in between doesn't interest me. Okay, so I am only interested in initial and final. Okay guys, so here if I have to calculate what is the work done by the conservative forces, that is nothing but minus delta u, that is equals to minus delta U gravitation plus delta U spring. That's what we have already seen some time back. So that is equals to UG initial minus UG final, all right, plus US initial minus US final, my dear students. Okay, so what is my UG initial? Let's have a look at this. Now for that, defining that particular part, I need to define which is the point that is having zero potential energy. So I will select this as the point of zero potential energy, my dear students. Okay. Now, if I select that, my UG initial is going to be my MGH, okay, minus, it has gone up to height x naught later down the line. So that becomes your mg x naught. Clear guys? Plus, what is my initial spring energy? 0. Because while this block is out here, it is at its natural length. So there is no compression, no elongation. So initial spring energy is 0. And finally, let's have a look at this. the spring gets stretched by x naught. Clear, guys? So that means this is half k x naught square. So this is my status out here. That is the work done by the conservative force. And students, there are no non-conservative forces. There are no external forces. So the work done by non-conservative and external forces is equals to 0. And students, all this will be equal to nothing but my change in kinetic energy. That is my delta K. Okay. Now students, initially, the block. What is K initial? The block is at rest. It is 0. And finally, when it comes here, it is a maximum extension. So at this point also, the block has come to rest. So K final is also equals to 0. So the change in kinetic energy, students, is going to be equal to 0. Simple thing. This is my equation number 2. And what was my equation number 1? This was my equation number 1. Whatever you got the value of your x naught, okay, so just insert it into this equation and you will be able to find out the height. So students, here mgh is going to be mg x naught minus half k x naught square. Students, I'll leave this still here for you guys, all right? And I think everyone would be able to solve this going ahead. I have the answer written down with me. If you solve it ahead, just check by putting the value of your x naught. The value of h comes to m square plus 2 small m capital M, okay, into g divided by 2k into small m. Okay, guys. So that is the height that from which I should throw that particular mass so that, okay, the bottom block loses contact with the ground. Okay, guys. So just that this basic idea should be clear to you, all right, of how the mechanics problem works and how the work energy theorem is embedded into it. And students' life is going to be like very, very simple. Okay, I highly recommend please put down the value of x naught and just check if you get this at the answer. Okay, that will also give you a reason to revise this particular question, which is a very, very important question, and it's appeared for previous years KVPY and also JEE mains examination. Okay, now guys, here I'm going to discuss with you a very, very important concept. Okay, which we have already mentioned or already stated, that is my work and energy, it is reference frame dependent. And through this particular problem, we are going to see how is my energy is reference frame dependent. Okay, now here they want us to calculate the elastic energy stored in the spring in the reference frame of this particular elevator. In the reference frame of elevator. Okay, students. Now, if I have to do it in the reference frame of the elevator, so where should my observer be, students? Definitely inside the elevator. So for all practical purpose, let's do one thing, students, without wasting much time. Let me just draw the situation all over again so that we've got bigger diagrams to analyze out here. We don't have to go into the small one. So let's see. So let's say this was its natural length and it kind of comes down. Okay. And this is its equilibrium position. This is its equilibrium position. Clear, guys? And students, as it has been mentioned, it is going up with an acceleration of g. It's going up with an acceleration of g. And this has got a spring constant of equals to 100, I believe. Yes, 100 Newton per meter. 100 Newton per meter. Okay, and this mass is 1 kg. Clear, guys? So that is what is given to us. My observer is inside the reference frame and is viewing all this. Okay. Now, students, as he is inside the reference frame, okay, if I draw the free body diagram of this particular block, what is going to be seen? At the equilibrium position means F net is equals to 0. The block has not come to rest at the equilibrium position. Remember that. Okay. It is only that F net is going to be equal to 0. So if F net is 0, what are the forces, by the way, acting on it? We will have one mg acting downward. Clear? Spring force is going to be acting in the upward direction. So that is like F spring. All right. And students, there is another thing that is going to be acting here, since the observation is taking from the non-inertial reference frame. Clear? So I'll have to apply a pseudo force. Pseudo force, students, is applied opposite to the direction of the acceleration of the reference frame. So which is the reference frame? My elevator is the reference frame. So where should I apply the pseudo force? I mean opposite to the direction of its acceleration. In which direction is it accelerating? In the upward direction. So where should I apply the pseudo force? In the downward direction? Very simple. Yes, my dear students, it's going to be applied in the downward direction. So that is my F pseudo. Equilibrium. Matlab F net is equals to 0, students. Okay. So here I can see my Fs minus Fp minus mg is equal to 0. Students, what is my spring force out here? Okay, it is nothing but, let's say the extension has been just x naught. So I can write it as kx naught minus spring minus the pseudo force. So the pseudo force is going to be mass of the body being observed. So that is like m into acceleration of the accelerating frame. So minus mg is equal to 0. Then here, students, I'll get the value of my x naught is 2 mg upon x naught, students. Okay, I get the value of my x naught. Then if I have to calculate the potential energy, it's nothing but half k x naught square. So that is like half k is like 100 into x naught square is going to be like 4 into m square g square into 100 square. Okay, students, so this will go 2 times. All right, 100 will go like 1 times. So overall mass is like 1. So that is like 2 into 1 square into 10 square upon 100. This and this is going to get deducted. So that is like 2 joules. So the potential energy in the reference frame of the elevator is 2 joules. Okay, guys. Now, what is going to be the potential energy in the reference frame of an inertial reference frame? Okay. If I consider an inertial reference frame, so let's say my observer is sitting here. So this is my inertial reference frame. Okay, guys. Now, from the inertial reference frame point of view, if I draw the free body diagram, my dear students, okay, how is it going to look like? There's a block here. At the equilibrium position, you only have k x naught acting here and mg. Will there be any other force if the observer is in the initial reference frame? No, absolutely not. There's no other force. So from this, it's the equilibrium position. X naught is going to be the same in that particular case. So kx naught is going to be equals to mg. Then, my dear students, my x naught will be equals to mg by k. Okay. Then in that particular scenario, the potential energy is going to become half k x naught square. That is nothing but half k is like 100 into m square g square upon 100 square, students. Okay, so in that case 100 and 100 is going to cancel out. Okay, m is equals to 1, so I can write this as half into 1 square into 10 square divided by 100. So this and this is going to cut, so that is equals to 0.5 joules, my dear students. So 0.5 joules if it is from the inertial reference frame, and it is going to be like 2 joules, my dear students, if it is for the non-inertial reference frame. Okay, guys. Now here, students, there was one question which was left in between. Okay, so let's just quickly have a short review on this. We wanted to find out the maximum elongation out here. Now here, just as I told you, first it is at its natural length, then it will go to its equilibrium position, equilibrium position. Students, it's not going to stop here. It's going to further go down, 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 such that it finally rests out here momentarily. It comes to stop. Okay? At the equilibrium position, remember students, that F net, the net sum of the forces is zero, but the block is not at rest. It still moves. It has got velocity. It still moves down and it kind of stops at a down position, and then it is being acted upon by the spring force in the upward direction. Okay. So during that time, because I have seen a lot of times maximum elongation के लिए students calculate it as kx equals to mg. That's why x is equals to mg by k. Students, this is absolutely wrong. Okay, when we equate the forces, no, that is not true. Rather, we'll have to equate the energy to solve this maximum elongation. What happens at the maximum elongation? Students, very simple. From its natural length, if I consider, and I consider this as my initial potential energy, that is equals to zero, and let's say it goes down by x naught. Okay, so here its potential energy U final will be minus mg x naught. Okay, guys. Then students, here initially the kinetic energy is equals to what? It is going to have some kind of a kinetic energy, all right, as it is going to kind of go down, all right. So if you say initially it is going to be at rest. It is not having any motion. Okay, I'm just like kind of holding it at rest, and due to the gravitational force, it is kind of going to go down. Okay, guys. So initial kinetic energy is also zero, and here finally when it stops at this point, the final kinetic energy is also zero. Okay, guys. Now, initial gravitational is zero, and initial final gravitational is also equals to like minus mg x naught. Okay. Initially, it is at its natural length, so U spring initial is equals to zero. And finally, when it is here, then is U spring final is going to be half k x naught squared. Okay, guys. So that is the entire idea we are going to use out here. So work done by conservative force is going to be like change in kinetic energy. So here there are no non-conservative, no external. So it's just a repetition of the same concept. So this is going to be equals to zero, which implies, my dear students, which is U spring initial minus U spring final plus U gravitational initial minus U gravitational final, students, and that should be equals to zero. Okay, students, if you kind of put down these values out here, U spring initial is basically zero, so that is like zero minus what is U spring final? What is U spring final? Half k x naught square, half k x naught square. Okay, plus what is U gravitational initial? It is zero. Okay, aha, I didn't need to do that. And minus what is U gravitational final? Minus mg x naught. Okay, guys. Now all that is equals to zero. If I kind of see this and equate it to zero, what is it going to appear like? It is simply going to appear like mg x naught is equals to half k x naught square, which is nothing but equals to x naught can be 1 x naught, and 1 x naught goes away. So x naught is equals to 2 mg upon k. All right, students, it's not mg by k, rather it is 2 mg by k. Okay, guys, here, so that is your work energy theorem and a few problems based on it. I hope you have taken a taste of it and enjoyed it at the same time. Okay, so now if you want kind of more exposure to these work energy problems and also other questions related to your work energy theorem and work energy power. All right. Do visit this link which is given out here. Okay, that is http://vdnt.in/work power energy. Once you click on this link, you will get to know more. When is this course on this particular work energy theorem is going to start? Okay, what are the prices and what are the timings? Okay, and you will get a short overview of what is the course going to be like, students. So here, Sumit Kundu. It was a pleasure telling you about all these concepts of work energy and why it makes our life simple as compared to if you have to do all these same questions by the force method. Okay, it gets a little tedious, guys. Okay, because forces are vectors, energies are scalars. So solving by energy method is kind of even simpler. Okay. So students, that's it for today. Thank you very much. God bless you all and see you in my course very soon. Okay, take care. Bye-bye.